Welcome to submodule 2 of 3 in Basics of Geosteering. In this session, we'll build a foundation for understanding how wells are steered within the reservoir. We'll explore the key components, techniques, and decision-making processes that guide well placement, setting the stage for deeper discussions in the slides ahead. In this submodule, we will review the primary techniques used in geosteering. These include the modelling, compare, and update method, and real-time dip determination using azimuthal tools. In the third and final submodule, we will look at distance-to-boundary methods that employ advanced remote detection technologies. Each of these techniques represents a different approach to well placement, with its own strengths and limitations. Well placement is at the heart of geosteering. We'll explore 3 distinct methods. Method 1, model, compare, update, uses conventional, non-azimuthal tools. Here we predict log responses before drilling, then refine our model by comparing those predictions with actual measurements. This iterative loop helps us understand if the well is staying within target. Method 2, dip determination takes advantage of azimuthal imaging tools. These tools measure formation resistivity, density or porosity in multiple directions around the borehole, which allows us to determine bedding plane orientations. Knowing dip and strike in real time provides a more accurate sense of where the wellbore sits within the structure. Method 3, distance to boundary, leverages cutting-edge remote detection technologies, often referred to as game-changing tools. These can detect resistivity contrasts far beyond the borehole wall, essentially allowing us to see ahead of the bit. This provides a significant step change in steering accuracy and decision-making. Each of these methods has different applications and limitations, which we'll explore through the upcoming slides. The first step in geosteering, defining the geological model. Before drilling begins, we must establish a clear structural framework of the reservoir. We do this by using offset well log data, seismic cross-sections, and formation tops. Offset logs provide property data such as gamma ray, density, neutron, and resistivity. These values allow us to characterize rock types and fluid content. Seismic cross-sections and formation tops help us visualize the regional structure. For example, where reservoirs dip or where faults are present. By combining these data sets, we define the true vertical depth, thickness, and dip of the target formation. This model serves as the baseline for steering decisions. Without it, real-time adjustments would lack context and we could easily drill out of zone. At the right of the slide, we see seismic cross-sections. On the left is the offset log data aligned with formation markers. These are combined to create a robust geological model that sets the stage for accurate well placement. On the next slide, we'll see how offset logs are used to define layer boundaries. Once we have offset well logs, the next task is to refine them through a process called log squaring. This involves taking the continuous log responses, shown here in green, and simplifying them into squared segments displayed in red. By doing this, we clearly identify layer boundaries and correlate them with formation markers, shown in black. Why is this step important? Real reservoirs are heterogeneous, but for modelling purposes, we need a simplified layered structure. Squaring allows us to match lithological changes more directly with geological surfaces, which makes forward modelling more reliable. On the image, the green curve represents raw offset log data, while the red squared profile simplifies these values into discrete layers. The black horizontal lines mark formation tops and boundaries. Interpreting this figure, we can see how continuous variations in the log are transformed into distinct zones that can be modelled more easily. This process leads us directly into constructing the property model, which is shown on the following slide. Once the property model is built, we refine it by defining the expected structure. This involves tying in offset wells and seismic data to understand how formations behave across the field. The key parameters we determine here are true vertical depth of target formations, their thickness, and the structural dip. These factors control reservoir geometry and directly influence the steering window available to us. By integrating well control with seismic horizons, we generate cross-sections that display how different formations relate spatially. This process reduces uncertainty, ensuring we know whether the reservoir is thickening, thinning, or changing dip. This structural framework provides context for our well trajectory. It allows us to plan where to land, how to drill laterals, and anticipate challenges such as faulting or dip reversals. With the expected structure defined, we can now move into the second stage of the workflow, generating modelled logs to predict tool responses along the planned well path. The next step is generating modelled logs. Using the planned well trajectory and the geological model, we simulate how logging tools are expected to respond. This is known as forward modelling. The inputs to this process are the well path geometry and the petrophysical properties assigned in the property model. The outputs are modelled tool responses, which can include gamma ray, resistivity, density, or other LWD measurements. Importantly, these simulations also account for tool-specific effects such as anisotropy, polarization, and borehole geometry. By generating these modelled logs, we create a baseline expectation of what the data should look like once drilling begins. This is critical because it provides a reference point for detecting discrepancies when real-time data arrives. In essence, forward modelling allows us to pre-visualize drilling results, improving our ability to recognize deviations from the plan. On the next slide, we'll see how this process continues with pre-job modeling. Here, we see the continuation of the modeled logs process. This step is typically carried out as part of pre-job modeling, before the bit enters the reservoir. Pre-job modeling involves running multiple scenarios based on possible variations in formation dip, thickness, or petrophysical properties. By doing so, we can anticipate what the log responses would look like if the well drills into different conditions. The goal is to prepare for uncertainty. If, for example, the dip is steeper than expected or a formation is thinner than predicted, we already have modelled log responses available to compare with real-time data. This reduces decision-making time during drilling and increases the likelihood of keeping the wellbore within target. Pre-job modelling also allows drilling and geosteering teams to discuss contingency plans, aligning everyone before operations start. With modelled logs in place, the next logical step is to compare them to actual drilling data as it comes in, which leads us into real-time data matching on the next slide. Once drilling begins, the real value of modelling is seen by comparing the actual measurements to our predicted logs. This process is known as real-time modelling. On the slide, the red curves represent the expected responses based on our forward model. The black, blue, and green curves are the actual logging while drilling data received from the bit. When these two sets of curves do not align, it signals that our original geological model may not reflect the true conditions encountered. This discrepancy can arise for several reasons. The structural dip may be different than anticipated, formation thickness may vary, or the tool responses may be influenced by local anisotropy. The key is that mismatches between predicted and actual logs trigger further analysis. Real-time matching is therefore an iterative loop: observe, compare, and adjust. It ensures that geosteering decisions are data-driven rather than based solely on pre-job assumptions. On the next slide, we'll see how the geological model is updated to reconcile these differences. In this step, we refine the model to better match the incoming data. The slide shows how the modelled formation is modified until the red curves, the expected responses, align more closely with the actual log data. This iterative update process is a cornerstone of geosteering. By continuously adjusting the geological model, we ensure that it reflects the real reservoir conditions encountered at the bit. The model is not static, it evolves with each new foot drilled. For example, if the wellbore encounters a formation boundary earlier than predicted, the model is updated to show a thinner layer. Conversely, if tool responses indicate a different dip angle, the structural surfaces in the model are adjusted accordingly. These updates feed directly back into steering decisions, allowing the driller and geologist to decide whether to hold angle, turn up, or drop into a new zone. On the next slide, we'll see how this process continues into a more detailed phase of matching real-time logs. Here we see the continued application of real-time matching. The process involves fine-tuning the geological model until modeled and actual data converge closely. This step is particularly important once the wellbore enters the reservoir section, where steering accuracy directly affects hydrocarbon exposure. As shown on the slide, the modeled formation is adjusted to bring the curves into agreement. By doing this, we confirm that the updated model reflects the true geometry and properties of the formations encountered. Accurate real-time matching enables proactive decision-making. Instead of reacting to unexpected data, we can anticipate boundary crossings, changes in dip or reservoir entry and exit points with greater confidence. This step represents the transition from purely diagnostic modeling to predictive geosteering, using the refined model to guide upcoming trajectory adjustments. On the next slide, we'll shift from the mechanics of matching logs to examining the outcomes of well placement, specifically reservoir exposure. One of the main goals of geosteering is to maximize reservoir exposure. This slide demonstrates how effective well placement ensures the wellbore remains within the productive interval for the longest possible distance. At total depth, a summary of the well confirms how much pay zone has been contacted. The accuracy of our steering decisions directly determines whether this exposure is maximized or compromised if the well is consistently steered within the sweet spot of the reservoir, avoiding shale breaks above or water contacts below. Hydrocarbon recovery is optimized. Conversely, poor steering can result in reduced pay, lower production, or even bypassed reserves. Reservoir exposure is not only a measure of technical success, but also of economic value. Longer exposure correlates directly with higher ultimate recovery and better return on investment. With this in mind, the next slide compares different placement outcomes, including a geometrical drilling alternative that highlights the importance of effective geosteering. This slide presents an alternate case model using purely geometrical drilling without geosteering adjustments. The key takeaway is that this approach results in significantly less pay zone being contacted. In this example, approximately 400 feet less reservoir exposure. The geometrical model assumes a fixed trajectory that follows planned angles without adjusting for real-time geological variations. While this approach simplifies operations, it ignores the complexity of the subsurface. If the actual reservoir dip, thickness, or position deviates from the model, the wellbore may exit the target zone prematurely. The comparison here highlights why geosteering provides such a step change in value. By constantly updating the model and steering the bit, we maximize productive footage, whereas a geometrical plan risks bypassing hydrocarbons. This example underscores the economic implications. Fewer feet in reservoir means lower production and reduced return. On the next slide, we'll revisit the different geosteering methods available and reinforce the strengths of each. Now let's move to method 2. Dip determination makes use of azimuthal imaging tools. These tools provide directional measurements around the circumference of the borehole, which allows us to resolve formation dips in real time. This adds a higher degree of precision for steering, particularly in structurally complex reservoirs. Azimuthal geosteering uses directional logging tools to measure formation properties around the full 360-degree circumference of the borehole. This allows us to see how the well is positioned relative to geological features, such as bedding planes or boundaries. In this example, the average density porosity is shown dropping. This change in porosity is an indicator that the well is moving relative to the target zone. The key steering question is, are we drifting above the reservoir, dropping below it, or pinching out? Azimuthal logs help answer this by showing not just average values, but their orientation relative to tool face. By analysing porosity or resistivity variations around the borehole, we can determine whether the well needs to be steered up, down, or held steady. The advantage here is increased steering accuracy, particularly in thin or dipping reservoirs where conventional logs may not provide sufficient resolution. Next, we'll see how this capability is made possible through LWD azimuthal imaging tools. Let's see how azimuthal imaging is achieved with logging while drilling tools. There are two main approaches. The first is to place several sensors evenly spaced around the circumference of the tool, such as in wireline tool systems. This gives continuous azimuthal coverage, but it requires multiple detectors. The second approach uses a single sensor, but with a precise understanding of its orientation relative to the tool axis. As the tool rotates, the sensor sweeps around, capturing data at different azimuths. This method is used in tools like GeoVision for resistivity and ADN Vision for density. In both cases, as the tool rotates in the borehole, we generate a full 360-degree image of formation properties. This capability transforms our ability to detect bedding dips, faults, and boundaries in real time. In short, LWD azimuthal imaging provides the data foundation for dip determination and more advanced geosteering workflows. Image resolution is critical to how well we can interpret geological features. This slide compares different bin counts for azimuthal imaging. On the left, you can see data segmented into quadrant bins, which is representative of tools such as the ADN, azimuthal density neutron, and RAB, resistivity at bit. In the middle are tools that collects data into 16 sectors around the circumference of the tools, which enables high resolution. Tools such as the vision tools provide this resolution. On the right, the GVR tool provides 56 bins, giving much finer detail. The difference is significant. With fewer bins, small-scale features such as thin beds or fractures may be averaged out, leading to a blurred image. With higher bin counts, those same features appear clearly defined, improving interpretation accuracy. This resolution determines how confidently we can identify bedding dips, detect faults, or track subtle reservoir boundaries. Higher resolution images therefore enable more precise steering decisions, especially in thinly bedded reservoirs. So the level of azimuthal detail has a direct impact on the effectiveness of geosteering. This slide shows a direct comparison between images acquired with FMI and GVR tool. FMI, a wireline tool, provides very high-resolution borehole images. GVR, an LWD tool, offers slightly lower resolution but has the major advantage of delivering images while drilling. On the left-hand image, open fractures are visible, cutting across the borehole wall. On the right-hand image, bedding planes are clearly defined. Both examples demonstrate the ability of imaging tools to resolve geological features critical to reservoir characterization. The key difference between FMI and GVR lies in application. FMI is excellent for post-drill evaluation, but it requires pulling the drill string and running wireline. GVR provides images in real time, enabling immediate geosteering adjustments. This comparison highlights the trade-off between ultimate resolution and operational timeliness. In practice, LWD imaging is the tool of choice for geosteering as it balances resolution with real-time availability. Once azimuthal images are acquired, the next step is interpretation. This slide shows the real-time image interpretation software, which is used to process images and identify geological features in real time. Azimuthal images reveal how formation features intersect the borehole. For example, bedding planes appear as sinusoidal curves across the image. The dip angle and azimuth of these beds can be calculated by measuring the geometry of the sinusoid. Similarly, fractures show up as sharp, linear features, often cutting across bedding. By interpreting these patterns, we can determine whether the well is drilling up structure, down structure, or staying level. This is critical for steering decisions, as it tells us whether we are drifting out of the target zone. The ability to interpret images while drilling means geologists and drilling engineers can react instantly, adjusting tool face or trajectory before bypassing hydrocarbons. Let's see how the azimuthal images show incidence angle, which refers to the angle at which the borehole intersects bedding planes. In the middle is the light brown formation structure, with the blue line representing the drilled path. On the left side, the images show drilling down the structure. Bedding planes dip upward relative to the wellbore, meaning we are moving toward the lower structural position. The sinusoid in the image is showing a sad face. On the right side, the images indicate drilling up the structure. The borehole is cutting bedding at the opposite angle, moving toward the crest. The sinusoid contrast on the image is showing a happy face. Remember this: dipping down is a sad face, dipping up is a happy face. Recognizing the incidence angle is vital. If we see the well drifting down structure, corrective action may be to steer up to remain within the pay zone. Conversely, if we're climbing too high, we may need to drop angle. In essence, image-derived incidence angles provide directional context that complements dip measurements. They tell us not only the bedding orientation, but also whether we're trending in or out of target. Let's take a moment to review the objectives of this sub-module. We examined 2 of the 3 key approaches: model, compare, update, and dip determination. In the final sub-module, we will look at the final approach, which is distance to bed boundary, and compare the different approaches. This concludes sub-module 2 on the basics of geosteering. Please proceed to the short quiz to test your understanding of the material. Thank you for your attention and engagement, and I look forward to continuing with you in the next sub-module of this training program.